So today is our SAP BW 7.3 session 2. Before we get started with our class, we can go through a quick recap. Let's not spend more than 5 minutes talking about what we have done so far, and maybe I can ask a couple of questions just to make sure that people are comfortable with the topics that have been covered so far. All right. So what the different topics that we have covered so far is, during the demo session we went through, I would say, roughly about an hour or two talking about what data warehousing is, what data warehousing tool is, and how is SAP BW defined as an SAP BW data warehousing tool. That is one concept that we have discussed. The other thing that we have discussed is we briefly went through the difference between an OLTP system versus OLAP system. What these different tools are, and why are they designed in a specific manner. So we have discussed that topic, but we are going to be touching upon OLTP and OLAP systems today. And then, so once we discussed on data warehousing tools and OLTP versus OLAP system, the next thing that we discussed was we started talking about the SAP landscape. So till about the last session, these are the primary topics that we have covered. Are there any open questions on these different topics? If there are any questions, please let me know. We can quickly do a recap. If not, I'll just give a quick overview of what we have done so far and then move on to our today's session. Any questions? Okay, let's move on. I'm going to quickly spend about like 2 or 3 minutes just giving an overview of what we have done so far, so David and Meera can benefit out of it. Okay, so let's say this is the data warehousing system that we are using. Let's not even go into what tool for data warehousing tool we are using right now. This is the data warehousing tool, and traditionally, if you look at any organization, an organization would have several transactional databases. Transactional databases are nothing but they store information at a very detailed level. So for example, if you take a bank transaction or a point of sale transaction, like when you buy something in a Walmart, what you would do is you would make a transaction to that particular entity. So in the case of Walmart, you buy something, that information goes into the system and stores in the table, in the database table. So let's say, for example, I made a transaction, let's say ABC. I bought a shirt for $20. So when I make this transaction, what I'm doing is I'm taking this data and storing it inside my transactional database. So if you look at the detail of it, it contains my name, the product I bought, and how much did I buy it for. And probably it will also include the salesperson's name. Let's say it is ZZZ. So this is the kind of information that is stored in any transactional database. It is very granular in level, and it just goes as and when we do the transaction, it goes and sits on the table. With the kind of data that is sitting on this table, we can only do a transaction level reporting, and that's why the system is referred to as an online transaction processing system. Online transaction processing system. As the name indicates, all we are doing is we are just processing a transactional level data. We take the information from the customer, we put it into the point of sale system, and that directly puts it into the database. So with this kind of information being available in multiple places, so let's say this is one Walmart which contains this information. There is another Walmart in Mexico which stores a similar information but in a different format. Let's say something like this, NCC. A shirt is probably referred to as something like that. Let's say XYZ is how it is referred, and in 50 pesos or something like that, data is stored. So this is the kind of format in which the data is stored in a different transactional basis. But let's say I am a manager who is responsible for the entire region, entire international, or probably for the entire organization. If I want to do an analytical reporting, I want to look at all these information and come up with intelligent reporting. Will I be able to do that by looking at these 3 different tables? It becomes very difficult, because what happens is the data that is stored in a particular region is stored in one format, and it is stored in a completely different format in another region in another database. So for me to go and look into all these multiple tables and come up with some analysis, doing analysis, and then on top of that, if I were to do a reporting, intelligent reporting, it would be very difficult, because first of all, the data is not designed or stored in the databases in such a way that I can use it for analytical reporting. It is only used for transactional reporting. So when I say a transactional reporting, what I'm talking about is I can only do simple kind of queries. So when I talk about simple queries, I'm talking about, okay, so today how many shirts did a specific region sell? I can go and look at this table because it is holding information in the description of shirt. I can just pull an information and write a simple query. So that's the kind of transactional reporting I can do. But if I want to do analytical reporting, when I say analytical reporting, I'm not only looking at today's data, I'm going to be looking at historical data. So let's say this summer, I'm trying to come up with a new product. I want to say maybe a beach kind of shirt. I want to market it. For me to analyze how this is going to be a success or not, I not only need what information is stored right now, but what I need to know is I need to look at what are all the beach shirt that has been sold this spring, but I compare it against my prior year summer and see how the trend has been. What did we do last year during summertime? What kind of shirts or what kind of products did we sell last year in comparison to this year? So what I'm doing is I'm doing a trend analysis. I'm looking at existing data. I'm also comparing it with my prior year data to come up with the logic. So for me to do that kind of intelligent reporting, it's not a straightaway report, right? I cannot just tap into this traditional database and say, okay, tomorrow beach shirts are going to be my next product for the summer. I cannot do that. I need a lot more information. So for me to do that, I cannot just hold the data in a transactional stage. I have to convert this data into something called as an MDM model. What it means is I have to take the data from this. I have to take a data from this table, all these multiple tables. These are commonly referred to as source systems, and I bring it into another system, and that's called the data warehousing. So what I do is I convert the data that is sitting from in these multiple tables, and I bring it into a common platform. This common platform will massage all this data, take them and put them in a common structure, so that a shirt in a specific region will correctly map to a XYZ object, which is also a shirt in a different region. So we are going to convert all this data and bring it into a common platform so that we have historical data stored in a system by which I can do my intelligent reporting. So in order to do this, what I'm going to do is, okay, so we understand that we need a common platform that can hold information. But what we have in our system is we have several transactional databases sitting across the globe. So when I talk about transactional databases, what I'm talking about is these are all built using a model called entity relationship model. Entity relationship model, and they are built for a specific reason, which is to write transactional data into traditional databases. But now I want to convert this ER model into a different model, and that model is called MDM model. MDM stands for multidimensional modeling. So what I'm doing is This data is useful for OLTP processing. So I'm converting the data that is in OLTP processing into a format called MDM, which is used for OLAP processing, which is online analytical processing. So I'm converting it into a structure that will be suitable for analytical reporting. So what I do is I create the model and I create the corresponding structures. So I know how I should be designing my common platform. I'm creating several tables here. Once I have done that, what I'm going to do is so this step is referred to as modeling. So the next step, what I'm going to do is, now I have understood what my design is going to be. I should actually start bringing data from my source system. So the second step is called ETL. ETL is nothing but extract, transform, and load. So these are the three. So what we are going to do is, now we have created a common platform. We have designed it such a way that it can accept data from the source system. Now the next step is establish connection to the multiple sources. I'm going to establish connection. Yes, Gurunath, you have a question?
What is MDM model? What does it mean?
MDM is multi-dimensional modeling, and we're going to get into that in few more minutes. If you could bear with me for 5 minutes, I'll get to that concept.
Okay, thanks.
So it's nothing but it's a different kind of modeling that is applicable for online analytical processing. So the second step is extract, transform, and load. So we establish the connection, that's the extraction to bring in data, transform. So for example, if I go back to my earlier screen, I said a shirt is described as shirt in one region and it is described as XYZ in another region. But I cannot be storing information in multiple formats within this common platform, because it doesn't make sense for me to aggregate data and provide analytical reporting. So instead, the business will come up with rules called as transformation rules or business rules. They will come up and specify what are all the things that we need to convert when we are bringing data from multiple places. So that is the piece called transformation. So we have established connection to extract data. We have applied the business rules that needs to be there. Now the final step is actually loading data from the source system into the data warehousing system. Once the data warehousing system has the data, now as a manager, what I can do is I can look into this data warehousing tool and create my intelligent reporting, because now I have historical data stored in my system. I can easily do my intelligent reporting based on the logic that is required or the business requirements that are given to us. So this is data warehousing concept. Any questions, David or Meera? I'm sure Meera, if you worked on Informatica, you should be well experienced with this. So it's open to all. Any questions? If not, I'll quickly move on to the other topics. So the biggest thing that we have is, now that we have established what a data warehousing tool is, the reason why SAP BW is referred to as the number one data warehousing tool is, it is referred to as an end-to-end data warehousing tool. End-to-end data warehousing tool. For example, what happens is there are so many data warehousing tools in the market which does one or two of the three primary functions that is required in a data warehousing. So if you take any data warehousing tool, there are three primary functions a data warehousing tool has to do, and the three functions are modeling, ETL, and reporting. So a data warehousing tool has to compulsorily do these three functionalities. What happens in a normal organization is a tool will not be able to provide all these functionalities. Let's say, for example, I bring in CA Irwin tool that is known for doing modeling purposes. So I have EAC, and then we have somebody from Informatica. Informatica is a ETL tool, and we could have reporting tools like Cognos, to provide our reporting needs. This is one way of doing data warehousing, where I look at third-party tools to get my data warehousing needs. But with this going through third party, there is a lot of limitation because I have to maintain 3 different softwares now instead of 1. So that's why when we go into SAP BW, what happens is all the 3, modeling, ETL and reporting, all of them are sitting within one application, which is SAP BW. If I want to do modeling, I have the tool within SAP BW. If I want ETL, I have the same tool within BW. Reporting, I have both BW tools and the business object tools that have been acquired by SAP is also now part of SAP system. So all the number 1 reporting capabilities are now available in SAP BW, and that's why SAP BW is always referred to as an end-to-end data warehousing solution. It can provide modeling, ETL and reporting. That's why it is called an end-to-end data warehousing tool. So that takes care of the data warehousing systems. Now let's quickly talk about the next topic that we discussed, which is SAP. As a consultant, the reason why everybody has joined this session is, or this batch is, you want to get into the SAP market. You want to start a career in SAP systems. So when you want to go into the real world as an SAP BW consultant, the primary reason why any organization would hire somebody for an SAP BW position is if the company has already invested a lot of money on SAP products. There are so many SAP products in the market. So a company typically would not just directly go into an SAP BW solution if it does not have SAP platform already established. Having said that, there are cases where SAP BW is used primarily as a data warehousing tool, but it is not associated with any SAP platform. But 99% of the time, when an organization is requiring a SAP BW consultant, they somehow or the other have a big SAP presence in their company. So what happens is, as an SAP consultant, SAP BW consultant, it is our primary responsibility that we know about the SAP landscape. Because when we talk to functional consultants, or when we talk to basis consultants, or when we talk to the organization itself, we should be making a lot of correct analysis and correct judgment about the tools and the landscape that is available in the system. So we should know what an SAP ECC system is. We should know what are the different products that are available in SAP, and that's what we discussed in the last session. So I'm not going to go into detail about what these tools are. Any questions, you can please go back to the session 1, and that has a detailed explanation of what the SAP system is, how SAP system came into existence, what were their initial strategy. During the 1970s and 1980s, SAP primarily focused on enterprise resource planning. They were completely focused on how to integrate the different departments in a company. So there is finance department, there is logistics department, there is human resources. It tightly integrated the different departments so that data seamlessly flows from one environment to the other environment. So that was the core concept during 1970s and 1980s. In the late 1990s, what happened is companies started moving global. They were not just focused on one region or one country. They started growing, expanding into international presence. So when that happened, they wanted to look at data from multiple countries and bring that data into one common platform and provide analytical reporting on it. So till about 1990s, late 1990s, SAP was primarily focused on transactional systems like SAP R3 system, SAP FICO module, AP module, and all these modules, for example. And then in the 1990s, with the internet era, when internet started booming, what happened is SAP wanted to get into the data warehousing technology. So during the 1990s, with the global era, SAP created something called as SAP BW, which is a data warehousing technology. This is to go across boundaries and bring data from multiple sources across the world into one common platform. So when this was done, They also created additional modules. So like for example SAP CRM, SAP SRM, all these different modules were created. These are nothing but the modules that were created during the 1970s were created for specific reasons. At that time it did not look into the internet era and build the system for accepting all that information. During the internet era, what SAP did was looked at the existing module. For example, SD, sales and distribution. Sales and distribution was completely focused on sales and delivery. It did not know what marketing was. It did not know what customer service was. So in order to fill those gaps, SAP came with an advanced version of SD, which is called SAP CRM. Similarly, several products were created, and that is how the market evolved. So 1970s and 1980s were referred to as the ERP era. 1990s to about 2000 was referred to as the My SAP Business Suite, which is the internet era comprising of SAP BW, CRM, APO, PPM. All these different modules came into existence. And then in 2004, what happened is SAP grew so big that it was becoming very difficult for users to actually log to an SAP ECC system, logging into a BW system, logging into a CRM system separately. So they wanted to come up with an internet framework that will help them use single sign-on concept. So SAP came up with a framework called NetWeaver. The NetWeaver is nothing but it is a framework that helps provide single sign-on. So if, for example, like a Yahoo or a MSN website, you go into one portal and you are having all the information like weather, sports, entertainment, all the information is sitting there. I don't as a user, I don't have to log into a specific weather website to understand what the weather is, or go into a specific sports channel or something like that. But internally, the website, though it shows all the information, it is underlying databases could be several applications. There could be several applications holding weather information, sports information, entertainment information. But for a user, it is transparent. I only see it as one place that contains all the information. So that's the concept of single sign-on. I log in into one place and I am able to access all my different systems. So that's the framework for NetWeaver. So when NetWeaver was created, an enterprise, so in order to make that single sign-on possible, they came up with a concept called Enterprise Portal. Enterprise Portal was tightly integrated to bring in all the information together in this. So when that happened, SAP decided that it makes more sense for SAP BW to be now tightly integrated with Enterprise Portal, and that's what happened. So this is, in a nutshell, the landscape of SAP. How the SAP BW system is connected to multiple SAP landscape objects, and how does a consultant work with all these tools. So this information will come handy when we start doing the hands-on. When we start extracting data from SAP sources, this will make sense. You will remember that when you go to the evolution of SAP, you will understand why SAP is now connected to ECC, or why SAP BW is connected to CRM or several other systems. So that's the concept of evolution. Any questions? So these are the topics that we have touched upon during the demo session and session 1. Now we are going to move into session 2. In today's session, what we are going to be talking about is, we are going to talk about two primary concepts. One is OLTP versus OLAP. What are the systems? And the next thing we are going to talk about is, we are going to talk about ER and MDM model. These are the two different topics that we are going to be covering tonight. The reason why I want to stress upon OLTP and OLAP system is, this is the fundamental of the data warehousing concept. If we understand what an OLTP and OLAP system is, and what the differences are and what the limitations are, then we can logically move from an OLTP OLAP concept into ER and MDM modeling. Once we understand the concept of ER and MDM model, that will be the foundation for SAP BW system course. Because if you remember, what we are going to do is, the primary focus of SAP BW course is to cover three main functions: modeling, ETL, and reporting. So the first logical thing that I would start is, as soon as we complete the ER model and MDM model, we will go into modeling. You will understand why MDM modeling is done, and that will lead us to understanding the modeling piece of SAP BW system, and that's going to be the course framework. If there are no questions, I will move on to the OLTP versus OLAP systems. Okay, OLTP versus OLAP system. First, let's talk about what OLTP systems are. So OLTP systems are online transaction processing systems. As the name indicates, they were created for holding transactional databases. Transactional database. Similarly, OLAP stands for online analytical processing systems. And they are related to multidimensional objects called data warehousing tools, data warehousing databases. So let's look at what the transactional database actually does. So as I mentioned in my previous example, a transactional, let's talk about a business requirement. Say for example, I'll take the example of Walmart or bank. I want to create a transactional system that will capture all my sales information. So basically what I want to do is, I want to create a sales application database. The nature of this database is going to be transactional in nature. I want to store information that will pertain to any sales that happens within the organization. So my intention is, what I'm going to do is, I'm going to create an application. So when I talk about an application always has two pieces. It has an application and it has a database. And a database. This is how normally any application would be referred to as. This application, the front end application, can be a Java based application, it could be a .NET based application, and the database can be Oracle, Microsoft SQL Server, or any kind of databases can be used. So when a company is spending money to design a transactional database, there are certain requirements they look for. Typically, if you look at it, a transactional database is very quick and fast in nature. So as a customer, if I'm purchasing an item in a Walmart or doing some transaction in Walmart, as soon as I make the transaction, I want that information to be stored in the database, and I want it to be stored in the lowest level so that it can quickly get into the system and get stored. So what are my primary, when I'm thinking about a transaction database, what are my primary goals? How do I want to design my database? I want to design it in such a fashion that, what are my core criteria? First thing is, the database has to be highly efficient to store transaction data. When I say highly efficient, I cannot wait for the system to do all the processing and only save the data 15 minutes from now. it has to be instantaneous. It has to be real time. As and when I make a transaction, the transaction has to go and sit into the traditional transactional database. What else can I do? I want it to be extremely fast when it comes to inserts, updates, and deletes. Because as again I said, the data has to be available now. So I have to insert the database table should be created such a fashion that I should be able to quickly insert the data, or if I'm making an update to an existing transaction, I should be able to do that update real fast, or if I'm doing any deletes, I should be able to do it very quickly. So these are the primary functions that I want to do in a transactional databases. So it has to be extremely fast. So if I want to have a highly efficient database and I should also have fast inputs into the system, what is going to be my leading next important criteria? The database should contain less volume of data. Imagine if I have billions and billions of records sitting in a transactional table. When I'm going to do an insert or an update, the table has to go through the process has to go through the entire table. I'm talking about all the billion records to see where this record already exists. If it exists, it has to go and update it. If it doesn't exist, it has to go insert a new record. So the system cannot be waiting long to make a transaction and save it. So the primary criteria is that the volume has to be very less. Again, so when this kind of data is stored in a transactional database, what is the purpose? What is the purpose of storing such information? The primary reason is I want to be able to look at this real-time data and do some kind of transactional reporting. The primary function of a transactional database is not for reporting. It is used for loading data into the system. The idea here is, as a customer, I get the data, I push the data into the transactional database. The system has to be designed such a way that it is quickly performing the save, input, insert, update, and delete functionality. But again, having said that, since we have already created a database, there should be some kind of reporting that should be available. And the kind of reporting that is available is called transactional reporting. When I talk about transactional reporting, what are the few examples that I can say? I can say, bring me all the transactions that has occurred for the month of May 2030. All transactions for May 2030. This is a very simple query. All I'm doing is I'm going into this database. The database already contains data stored in a very detailed level. It's just going looking for the month of May and bringing all the information. That's a very straightforward information. It can be brought in. Okay, let me take the scenario of a bank. If you typically go into your web-based account, into a banking account, typically if you look at your system, you can only bring in transactional data for, let's say, 30 days or maybe 60 days. Because the transactional level data is only stored for a very small amount of volume and data and time. If you go and ask that you want to look at data for 6 months prior to 6 months now, you cannot directly take it from the transactional database. You cannot do it from a web-based account. You have to put in a request into the system and they will email the information to you. So that's why the reason is they want to keep this transactional database as a very small system so that you can it's highly optimized to load data into the system. Since there is very little data sitting in the transactional database, I won't be able to do any fancy kind of reporting. So when I'm talking about fancy reporting, so few minutes back I explained a scenario where I want to look at the shirt information that is stored for this May, and I want to compare it with the prior year of May of 2012. I want to look at the data and see what is going to be my biggest product for this year. I have to come up with an analysis and say, okay, so I'm doing a trend. So that is looking back into several years and getting information. That is trend analysis. On the other hand, what I can do is I can look at the data that is available in my system, which is the historical data, and I can start forecasting. I have looked at a trend. This is what I think has happened in the year. Now with the information that's available, I'm predicting my future. This is going to be my next big thing that's going to happen. So this is nothing but a multi-dimensional analysis. I'm going to be looking at intelligent reporting using multi-dimension modeling or multi-dimensional analysis. So for me to get this kind of information, the data that is stored in a transactional database is not sufficient. So I have to look into a different model that will help me achieve my results. So that's why every company slowly started moving from a online transaction system into a OLAP system. When I say companies started moving from an online transaction to an online, they didn't make this obsolete and move into online. This has a specific reason as to why it is in the company, and online analytical processing system also has a specific reason why it is there in the company. If the company's primary focus is to store transactional information into the system, they will be heavily invested in online transaction systems. But at the same time, if they want to compete with their competitors, they have to be sharp and get analytical reporting from the data that is stored in their system. So they have to also invest and move into another different area, which is called online analytical processing system. Use that for multi-dimensional analysis and come up with all data that is business intelligent decisions to be succeeding in the market, to be getting a better market share in the products that they are manufacturing. So this is the high level difference between an OLTP system and an online analytical processing system. So I have a PowerPoint that quickly talks about the difference between the two systems. So let's quickly take a look at it. Are there any questions at this point before I move on to the slide? Are there any questions? Okay, all right. So now let's talk. Can everybody see my screen? I don't know if it's a little small font, but the idea here is we are going to be talking about OLTP and OLAP systems across different concepts. Yes, Gurunath, you had a question?
Yeah, what's the difference between MDM and MDA?
MDM is the kind of model that is used to get analytical reporting. So it is like for a lack of a better term, it is like a mechanism that is used to design the business requirement. It's a OLAP. It's for any OLAP system, I need a multi-dimension model that will take the business requirement. So as let's say I'm a CIO of a company, there is a new requirement saying that I have several transactional databases sitting in my system. I want to use that data to provide business intelligence reporting. So they are saying that, okay, let's start looking at all the sales applications that are across the country, bring it into a common platform, use that for analytical reporting to see which are all the sales targets that we can look at. So this is just a simple example. So for me to do that, I need a mechanism. I cannot just take the transactional table and say that, okay, from tomorrow onwards, the transactional table is going to become a data warehousing table. It's not a switch, right? So for me to logically convert data that is residing in a transactional database into a common platform, I need a mechanism, I need a driver that will do it. So the driving mechanism is nothing but multi-dimension modeling. That is multi-dimensional modeling. Multi-dimensional analysis is, see, if you look at the previous example I had given, a transactional reporting, I can only do a linear reporting on a transaction. So I can only look at it from a single point. I can say how many shirts did I sell this month, or how many shoes did I sell this month. It is only based on, it's like a single dimensional view. I'm only looking at one object. Oh, Are you having trouble hearing my voice? Gurunath, if you don't mind, can you mute yourself? I think when there is another person who has unmute the mic, I think there are some issues. Can you hear me better now?
Yeah. Yes, I can.
Okay, thank you. Yeah. So when I'm talking, if you don't mind, can you please mute yourself so that I think there's some you'll be able to hear me better. Okay. So what I was thinking is, when in a transaction database, I'm only doing a linear type of reporting. I can only get very small kind of information. I can do a mix and match. Oh, again, is there a problem with my any problem? Now,
I can hear you well.
how about Sam? Can you hear me now? How about Mutahira? Can you hear me?
You're breaking up. I can hear you well.
Okay,
I
give me
can
1
hear
minute.
you well.
Give me 1 minute. Let's just reconnect to my mic. Okay, give me just 1 second.
Okay.
Can you hear me now?
Yeah, I can hear you now.
Okay. Yeah, please let me know if my voice is breaking up. So that's it. When I talk about transactional reporting, my reporting is only a single or two-dimensional information. I'm only looking at, okay, what my shirt has done or what my last month transaction has been. So there are no varieties to it. I'm not able to look at the data from multiple angles. I'm not able to look at it from multiple angles. But what I can do is, if I want to look at the data from multiple angles. So for example, let's say I have a scenario where a salesperson sold a material to a customer. So there is a sales transaction that has happened. So if I want to look at it from a salesperson standpoint, I can do analysis from a salesperson standpoint. If I want to analyze it from a customer standpoint, I can look at it from a customer standpoint. If I want to look at how the materials are doing, I can also look at the same data from a material standpoint. So what I'm talking about is I'm looking at multiple dimensions. I'm not looking at the data from just one perspective. I'm looking at it from multiple perspectives, and that is called multidimensional. So I'm analyzing the information that's stored in the system from multiple angles, and that's why the system is defined as multi-dimensional modeling or multi-dimensional analysis, analyzing the data that is stored in a data warehousing system from multiple angles. So did that answer your question, Gurunath? Yes, Sanjay. So SAP SD, all the ERP systems that are created, that are available in the market, are transactional in nature, because if you look at it, the primary functions of all the ERP systems are to store the information in an efficient manner, so that it can use the data for inserts, updates, and deletes very efficiently. So you are very correct. It is used for SAP ECC system, SAP SD, SAP MM. All of these are referred to as OLTP systems. Sure, no problem. So that talks about my OLTP system. So now let me quickly go into my slide. So let's talk about the quick differences between OLTP system and OLAP system. When I say there are differences, it is not necessarily meaning that one is bad and one is good. That is the wrong misconception. What we are trying to do here is we are trying to appreciate what these two different systems are doing and what are they built for. So if you look at the first concept, which is source of data, if you look at an OLTP system, since the data that is going and sitting in the system is OLTP in nature, it's transactional in nature, My source data is also going to be transactional in nature. I make a bank deposit, that is a transaction. That transaction data goes and sits into my OLTP system. I make a sale transaction in Walmart, that data goes and sits in. So if you look at it, the source of data is operational in nature. It is transactional data, and the source is also transactional in nature. Let's look at the OLAP system. Why is the OLAP system designed? It is not used to just store transactional level data. That is already being done in OLTP system. There is a primary reason why OLAP systems are built. It is to take the transactional data from the OLTP system, load volumes and volumes of data into the system, that is historical data into the system, and consolidate the information. When I say consolidate it, I'm going to pull data from US, I'm going to pull data from India, I'm going to pull data from China. I'm consolidating all the information together. I'm not going to be looking at one data, one transaction or one record. I'm consolidating all the information so that I can detect information. I can deduce information from the system, from the consolidated information that's available in my system. So the nature of the data itself is it's consolidated. When I say consolidated, it is summarized. I'm not going to be looking at what did one person buy this today. That I can do it in the OLTP system. But I'm looking at a larger information. I'm looking at summarized high level information that will help me do analysis, analytical reporting. So that is the source information. Let's look at the purpose of the data. What is the purpose of the data in OLTP system? The primary reason why we store OLTP information is to store transactional data efficiently with quick updates, deletes, and inserts. So it says to control and run fundamental business tasks. What is my business task? My revenue is generated only when there is a sales transaction happens, right? So my purpose of the transactional database is to get that information stored in the system so that I can track my revenue for day-to-day basis. But in the case of an OLAP system, it is not to run business on a day-to-day basis. If I want to do day-to-day activity analysis, I'm going to be looking at my OLTP system. But I want to plan, I want to do problem solving, and I want to help in decision supporting systems. For that, I don't just need the day-to-day activity. I need holistic view of my data so that I can plan for my future. I can, if there are any issues, I can look at the historical data that is sitting in the system and come up with solution for my problems. Or I can use it for decision support. So that's the data that is for OLAP system. Processing speed. As I said, the data that is being transaction in nature has to be quickly stored in my database. It cannot be processed for a very long time. So it has to be instantaneous. It is real-time data. I make a transaction, it goes and sits in the system. I make a bank transaction, I come home and I look at the system, I should be able to see the transaction right then and there. But let's look at the OLAP system. When I'm talking about OLAP system, my necessity is not to look at day-to-day activity. So if I made a bank transaction and I go into the OLAP system and expect it to have that information, it is not going to serve me a purpose. What is the purpose of having an OLAP system? I'm going to be doing predictive analysis. I'm going to be doing analysis over a large amount of data. So if you look at processing in the OLAP system, processing is definitely important. We have to load information from transactional systems into the OLAP system, but it is referred to as near real time. It is not real time. Any data warehousing system is expected to have a delay. If a transaction happens in an OLTP system, there is a specific delay that is explained to the business organization, saying that okay, we have a timeline of 5-hour gap by which we pull the data into the OLAP systems. So that is completely understandable because I'm not going to do analysis on today's data. I'm going to take today's data, club it with several months or several years of data and do analysis on top of that. So if you look at it, it depends on the amount of data involved. Batch data refreshes and complex queries may take many hours. Because when I'm bringing data into my OLAP system, I'm bringing larger volume of data. I cannot be doing high processing loads into my system. So that's the difference between OLTP system and OLAP system when it comes to processing. Now let's look at the database design. This is one of the primary reasons why we have OLTP systems and OLAP systems. When you look at the database design, transaction data, as I said, the inserts, updates and deletes should be extremely fast. We go into something called as highly normalized database. When I talk about highly normalized, there is I don't know if you have heard about the normalization forms. Any database design has to adhere to normalization technology. There is first normalization form, second normalization form, and third normalization form, and further. Excuse me. So normally when a OLTP system is designed, it is primarily looked at for normalization, because the idea is to save the data quickly, and it should be in a form that it can be added or updated very quick and very efficiently. So for me to do that, I cannot just say, okay, my company is giving me a requirement that I have to create a sales application. I need a salesperson information, so I'm going to create a table for salesperson. I need some information on materials, so I'm going to create a table for materials. And I need some information on a customer, so I'm going to create a table for customer. That's fine. But what's going to happen is, when we start looking at these tables, we'll understand that there are some lot of redundant information being stored in the table. So when we talk about redundant information, the time to process the table or add data or update data is going to take longer time. So what happens is, when a database is being designed, and that's when we talk about ER modeling, we're going to talk about what is normalization. How is it going to help create efficient database tables to store data? So that is OLTP system. Now let's look at OLAP systems. An OLAP system is typically denormalized, because if you look at it, I am reading data from an OLAP system. I'm not writing, I'm not inserting or updating or deleting information in an OLAP system. I'm collecting information so that I can efficiently read the data. So when I'm reading the data, it doesn't really matter if there is data redundancy in the system, because the data warehouse is designed such a way that it can accept large volume. It is meant to hold larger volume of data. So the primary concern here is not volume. It is a given that data warehousing solutions are going to have terabytes and terabytes of data. So they're not going to worry about, is the table efficiently designed so that it can load data into it. It is highly denormalized. Highly denormalized in the sense that the effort is put more into how efficiently can we read this information. It's not how efficiently we can write into these tables, because it's not real time. I'm not asking the data to be there right then and there for it to be efficiently writing into the system. But what is my requirement is, I should be able to quickly read the data to provide analytical reports. So that's why it is highly denormalized. Backup and recovery. Backup and recovery. See, transactional data is the bread and butter of any organization. If I lose my today's, for some reason, I lose a month of data that is stored in my transactional data, there is no other way I can go and get that information, right? If there is no proper backup or archival process for my data, data lost is lost. I cannot get back that information. But if you look at the OLAP system, it is an additional layer on top of my OLTP system. I'm having historical data that is being stored. For some reason, if I lose a month of data or something like that, if the data is still available in my OLTP system, I can always re-pull that information into the OLAP. So when it comes to backup and recovery, it is very rigorous when it comes to OLTP system. When I say that it is rigorous in OLTP, it does not mean that we don't do it in OLAP. OLAP also we do it, but what we do is we spend more time on data archival. Let's say I have 5 years and 10 years of data sitting in my OLAP system. I'm not going to, as a company, I'm not going to be looking at what happened in 10 years, because the technology is moving so fast. I don't have to look at 10 years of data to understand what my future is going to be. I will make a business decision saying that okay, I don't want to store anything that is over 3 years, so I will archive that data into a disk or something like that. So definitely there is backup and recovery needed, but it's not as critical as one would require for an OLTP system. Age of data. Typically it is a current data because we are looking at real-time data. We want to know what's happening now in the system. But the primary reason of an OLAP system is it is to analyze data. So for analysis purpose, I need not only current data but also historical data. So that's the kind of data that is stored in OLAP. Queries. So as I said, the queries are meant to be very simple in nature when it comes to OLTP system. It is just going to generate a simple query and simple information that's going to come out of the system. But if you look at the queries that are developed on OLAP system, it is all very complex in nature. I'm trying to come up with something new. I'm going to use the data that is available. I'm going to create ad hoc queries that will help me predict the future or look at the trend. So it's going to be very complex queries. Database operation. So primarily if you look at it, insert, modify, delete and update are the primary functions that happens in an OLTP system. In an OLAP system, primarily we are focused on reading. Most importance is given to reading the data. How quickly can I read the data to do trend analysis? I'm looking at multiple years of data, but I don't want to be sitting and waiting 1 or 2 hours to get the data in a report. I want to be able to read it just like that so that in 5 or 10 seconds I'm able to massage all the data that is available across years and bring it into a report. So that's the main purpose. What kind of data is being revealed? It's a snapshot of my business process. So what is happening now in my system? That's what OLTP provides. OLAP system provides multi-dimensional analysis of data. It is looking at the data from several perspectives and bringing me read information. It's bringing me report from multiple perspectives. Data set. Normally, it's not actually correct that we use 6 to 18 months. In a traditional world, what happens is we store about 2 to 3 months of data in a system. But in OLAP system, since the main reason is to hold historical data, we look at anywhere between 2 to 7 years of data that is stored in a system. So these are the primary differences between an OLAP and OLTP system. This is very essential because when you start working on SAP BW, you are bringing in data from several source systems, several OLTP systems. For you to understand and convert the data and bring it into the OLAP nature, you should know the reasons why certain things are being done. Okay, now I'm bringing data from an OLTP system into my OLAP system. What is this reason why I am bringing it? I am bringing it for reporting purposes. I'm bringing it so that it can be quickly read to provide data. So this slide provides a clear information of what an OLTP system does and what an OLAP system does. What are its differences? How does one complement the other? And that's what we are doing here. So any questions on this? So this covers our OLAP and OLTP systems. Any questions? Okay. So if there are no questions, I will move on to what is the next concept, which is ER model. Let's talk about ER model and MDM model. For SAP BW, for anybody who is going to be working on SAP BW system or no matter SAP BW, I'm talking about in general data warehousing, it is a must that they should know MDM modeling. MDM modeling is the foundation for any data warehousing tool. No data warehousing tool cannot function without MDM modeling. It's the prerequisite for data warehousing. So we could have started this session talking directly about MDM model and go into SAP BW for us to get a better understanding. there should be a reason why we are doing MDM model, right? So there is an already existing model that is very popular in the market. So there should be some reason as to why we are jumping from an ER model to a MDM model, so that can be used for OLAP systems. So that's why we are going to quickly cover ER model, the limitations of an ER model, and jump into an MDM model to show how multi-dimensional analysis can be done using an MDM model. So having said that, the primary focus of this batch or this training is not to be talking about ER model. It's going to be talking about MDM modeling and OLAP system. So I'll briefly touch upon the ER model, give an understanding of what an ER model does, and then we'll show an example in ER model and show that same example as to how it is converted into an MDM model and how it is used in a OLAP system. So that's going to be the primary. The remaining of today's session is going to be focusing on ER model, MDM model, how it is getting converted from one to the other. That's going to be our next session. Okay, let's talk about ER model. As the name represents, E stands for entity relationship model. Prior to OLAP systems coming into existence, all organizations were focusing only on OLTP systems. So all the OLTP systems required a designing technique that would help design all the databases needed for transactional purposes. So all OLTP systems used a certain modeling concept called entity relationship model. Even now, if you go into a traditional database system, all the tables that are designed in a traditional database, maybe it's Oracle or Microsoft SQL, they are built by the concept of entity relationship. So it is a mechanism or it is a driver that helps create databases. Okay, so we can ask, why would we need an ER model? Why can I not just take a business requirement and directly create a table, right? That's very quite possible. Business comes with the requirements and business says that, okay, I have to create a new sales application system. These are the things I'm looking for. Go create a table. The biggest problem with that is, and I'll explain how that works. So let's say a business is doing a new application called sales application system. They want to create a new sales application system. So for that, they want to create a database that will help them store the sales level data in that system. For the business to give us requirements, so let's consider ourselves as purely technical people. We are all the database developers who are going to be working on the database system. I don't speak a language that the user can understand. If I start talking about tables and fields and structures and all that, the user is going to be lost. They will not understand what we are talking about. So there has to be a middle ground. There has to be a common terminology that can be used that is both understandable by a technical person and also appreciated by a business team. So that's why what happened is business users will define their, so this is business users will give their requirements. They give their requirements, and the requirements are converted into a concept called model. Model is nothing but a logical design of the business requirement. So in this example, let's say business wants to create a sales application. So they are saying that my primary objects are, I need a sales person information. I want to store material level information. I want to store customer information, and I should be able to tap into all these three different information and come up with a data or a system that can store a transaction. If just by having a salesperson I cannot do any transaction, just by having material alone I cannot have any transaction, by having customer alone I cannot have any. I should have all the three systems interact with each other. A salesperson has to sell a material to a customer, only then a transaction happens, right? So the connection has to happen. For this connection to happen, what will happen is the business will say my sales application is such that it should, the primary stakeholders of this application will be that I'll have some salesperson information, I'll have some material information, I'll have some customer information. I want to put them into a database so that they interact among themselves and they create a transaction table, transactional data that will be stored in the system. That is all the level of detail that a business will give. So for us to understand, what they will do is they will give it in an English, in a layman's term. They will just talk about business terms, and modelers or database developers, what they will do is they will look at the business requirements. So let me go into a new slide. So this is the business requirements provided by the users. So what we do is we come up with something called as, we use the famous modeling technique that is available for transactional system, which is entity relationship model, and we create something, a design, a logical design. So what we can do is, in an ER model there are two types of model, logical and physical, and I'll quickly talk about what those two mean. So for the time being, let me just talk about the concept. I'm not going to go into specifically about what logical or what physical is going to do. I'll quickly, once I've explained the concept, I'll explain what it is. I'll take the business requirement and I understand it. I'm saying, okay, I have understood that the company needs something for salesperson, something for material, something for customer. So in an entity relationship model, there are sequence of steps that needs to be done. First thing is, so now we understand what an ER model is. An ER model is nothing but taking the business requirement that is given to us in business term and representing it as a logical design. I am coming up with a design which I think helps solve the business requirement. So for that, what I have to do is I have to define all the entities required. So when I talk about entities, what I'm talking about is, so let's say the business requirement says that we need to create a sales application that will show the interaction between a salesperson, material and customer to define and store the transaction level data. Okay, with this English term, what I understand is there are some primary players or primary entities that are required in the system. So let's look at what are the primary entities. I need salesperson information, I need material information, and I need customer information. So right now this is the first level of information. I have defined all the entities that are required for my system. I need a salesperson entity, a material entity, and a customer entity. So when I talk about entity, look of it as a business purpose. A salesperson is a business purpose, a material is a business purpose, and a customer is a material is a business purpose. Once I have identified my entities, the second logical step in an entire entity relationship model is find the association between the different entities in the system. find the association between entities. So when I say association, or I can also refer to it as relationship. And now you would have understood why it is referred to as entity relationship model. I am identifying all the entities. I am now finding the relationship between the entities. So how do I define the relationship? As a let's take an example of a Best Buy or something like that. Let's say I am a salesperson. I can interact with one customer, or I can interact with many customers, right? As a salesperson, I can interact with one customer per day, or I can interact with several customers per day. So the relationship between a salesperson and a customer is referred to as one to many. One salesperson can be associated with any customer. But if you look at a customer normally is on a given day is interacting with only one salesperson. So the relationship from a customer to a salesperson standpoint is 1 to 1. One customer will deal with one salesperson. Now let's look at material. A salesperson can sell one or many materials in a day. So the relationship is 1 to many again. Now let's look at the relationship between material and customer. One material can be bought by many customers, and many customers can buy many material. So it's a many to many relationship. So what I'm doing now is I'm just establishing the relationship between the different entities in the system. What happens logically is when the when the different entities starts interacting with each other, a new concept arises, which is what happens when a salesperson and a material and a customer interact with each other. When the relationship is built, we create a new thing called as a transaction. What happens is a salesperson interacts with a customer and he sells a material to that customer. So I've established a complete circle with all my entities, and that information gets stored in my transaction. So look at the data that can get stored. So I am a salesperson 100. I am selling to ABC, that's my customer, and I was sold material M100 for $500. So that has happened between all the entities. So this interaction goes and sits in my transaction entity. So this is how the relationship is established. Now we have defined the first two logical steps of an entity relationship model. We have defined the entities required. Initially there are only 3 entities defined. Once they start interacting among themselves, another entity is created which is called transaction, and that transaction only happens if the entities interact within each other. Now second step, we have identified the association between the entities. The next step is, now that I have established connection between all but I need to know more information about each of my entity. I need to know define the attributes of each entity. When I say salesperson, I'm not an entity that's just salesperson. I don't have any other connection. That's not the case. So let's look at what can be an attribute of salesperson. So before describing that, let's understand what an attribute is. Let's take customer. If I am a customer will have an address. The customer will have a name. The customer will be associated with a country, region, city, state, all that information. So attribute is nothing but additional information about an entity. So customer, let's say the customer value is ABC. If ABC is the customer, ABC should have additional information about it, right? I cannot just say customer ABC and it doesn't make any sense. Customer ABC lives in Naperville in Illinois, and this is the phone number of this customer. Once I give additional information, it makes more meaning to the customer. Now I have more meaningful data. So that is what is called attribute. So every entity will have attribute associated with it. So that is customer. Customer can have customer name, first name, last name, phone numbers, address, bank account number, a shipping address, billing address. All that information can be stored for a customer. Similarly, a salesperson can be associated with a region. A salesperson can be associated with a sales group. So there can be a lot of attributes for a salesperson. Again, a material can be assigned to a material group, and it could have pricing, what the price of a material is, what is the quantity, is it a single item or is it a pack of 12 items. So these are all the additional information that are associated with an entity, and that is called attribute. So these three steps, we define the entities, we define the association between them, and we define the attributes of each entity. Once we do this, we have created the first step of entity relationship model. So now what I'm going to do is, in a new slide, I'm saying that I have created customer, I've created material, I've created salesperson. Each of it has some additional attributes. Let's say I have customer name, address. So these are two examples. Again, for material, I have material group, material type. For salesperson, I have sales group, sales region. These are just examples of attributes. I have also established my relationship. I know what my relationship. Is there a question? I see that call in user 9 has unmuted. Is there a question? If not, can you please mute yourself? Okay. So now the next step, logical step, is we have also associated each of these entities with each other. By associating all of them, we also created a new entity called, let's call it sales order. The moment customer buys a material from a salesperson, a sales transaction is happening. So that is also connected. So we have done this now. So what happens is, this is called a logical ER model. If you look at it, I have not created any database tables. I have not created any attribute fields for my table. I have not connected all these tables. I'm only representing the data that I have taken from business requirement, and I'm putting it into a paper as a logical display. So when I create this logical display and I give it back to the users, business, though they don't understand databases, they will be able to look at this relationship. They can look at it from a box standpoint. They'll say, okay, my customer is interacting with material, my customer is interacting with a salesperson. So when salesperson, material, and customer interact within each other, they're creating a sales order. A customer has all these attributes, material has all these attributes, salesperson has all these attributes, and they are all connecting together to form a sales order. This is very useful for a user to understand, because the user cannot understand this database terminologies. If I say I am using a primary key in my database table, these are my attributes, these are not primary keys, they are not going to understand. So they want something called as a logical model. With this information, as I specified earlier, a transactional database is designed specifically to be highly normalized. When I talk about normalization, I'll quickly go through what normalization is. I'm not going to spend too much time on normalization because that itself can be like 5-6 hours of sessions. So let's not dwell deep into it, but I'll give a quick information. One is first normalization form. First normalization form is nothing but look at your entities, that is look at your table and see if anything is redundant information. If there is too much information that's available in the system, you want to take it out, take that information out of this table. So eliminate redundant data. So that's going to be the first normalization form. So let's say I have customer data, right? So let's say the customer is associated with a lot of attributes. I have customer name, first name, last name. I have customer shipping address. I have customer billing address, and I have customer postal address. So there are 3 addresses associated with this customer. So if I were to create a table based on this, what I will do is, this is how my table structure is going to look like. Customer name, ship address, bill address, postal address. If you look at it, though the names are different, ship address, bill address, and postal address, these are all address in nature. So if I'm going to create 100, name is ABC, address is 1001 FXG Lane or something like that, and billing address I'm creating as 2000 something, and postal address I'm creating. So what I'm essentially doing is I'm using the same kind of data and storing redundant information. So in order, what I can do is I can eliminate redundant data, take away, look at this, this is unique data, this is not redundant, this is unique data that is not redundant. If you look at the shipping address, billing address, and postal address, the concept is they are all addresses. So what I can do is I can remove this information. I can put them in a different table altogether. So what I'm going to do is I'm going to create 2 tables, customer and name. So that will hold 100 ABC, and I create one more table which contains address, let's say customer number, customer, and address, and it will also contain address type. So now I can store unique data in this table, and all I have to do is, so here I'll say 100, address is 1001, and my address type is ship address, and similarly I'll create another entry. So what I'm doing is I'm eliminating redundancy. I'm storing minimal information in one table and minimal information in the other table. If I want to connect the customer with address, all I have to do is look at the 100 here and look up the 100 here, and I will be able to bring up my additional information. So that is first normalization form. Let's look at second normalization form. So I'm not going to, I think we are running out of time, so I'm just going to quickly look at what second normalization form does. So let's take the same example. So now we have eliminated data, but similarly if we find this shipping address, let's take the same example. Shipping address is not only used by customer. The same shipping address can be used by a sales order. When a sales order data is loaded, I want to make sure that a sales order is shipped to a specific address. It is billed to a specific address. So I'm repeatedly using the information address. It is used associated with a customer. It is also associated with a sales order entity. So what I'm doing is I'm looking at what are all the common things that are being shared by different entities, and I'm putting it in a separate table. So now what I'm going to do is I will create a sales order number. So what I can do is I can use the same table for customer. I can also use it for sales order information. So I'm grouping all the required entities, attributes that are used across multiple entities, and I'm storing it separately, so that I can, as a customer, I can look into that information. I can, as a sales order person, I can use it. As a salesperson, I can look into this information. So it is stored separately. So that's the concept of set normalization. Looking at set values of information that are used by multiple entities and move them separately so that they can all individually use it. The biggest reason why we would do this is, let's say for example, I use without first normalization form, I keep the data like this, and then I also have another table called sales order, and I have the shipping address and all that information stored there also. For some reason, this customer, the shipping address has changed from 1001 to 10,001 or something like that. I have to go change it in the customer table. I have to go change it in the sales order table. Maintenance becomes a nightmare. I have to do it, and I should not make mistakes when I do it across multiple tables. But if I store all this information in one common entry, when I want to make a change, I just make it in one place, and it is applicable across all the tables. That's the reason why we are normalizing the data. And then there could be other reasons. The third one is third normalization. Third normalization. So third normalization is, let's say for example, I have a table, customer, material type. Just an example. A customer 100 bought a material M100. The M100 is a plumbing material type. This is how my table is stored, and my primary key for my table is customer. A customer is directly associated with the material because as a customer, I bought this material. So there is a direct relationship to my material and my customer. But look at material type. The material type is directly associated with the material, but it has no connection to the customer. So if a table has a field or an attribute that is not directly related to the primary key of the table, that is what term normalization form talks about. Look at all the attributes in a table. If they are not directly related to the primary key, put them in a separate table. So in this case, I would probably have a material table, and the material table will be connected to my material type. If I want to know the material type, I will jump from a customer to a material, and from material I know what my material type is. So this is what normalization is about. Whenever we are doing a transactional database design, the primary focus is we want to adhere to first normalization and second normalization. Definitely, we want to try for the third normalization also. In some cases it might not help because of the complexity of the business requirement, but we try and do the normalization on a transactional database. It is good from a technical standpoint, but now let me quickly go back. Then I created my logical design. Yes, Sam, you have a question?
Yeah, I'm sorry, I haven't understood the second normalization part of it. Can you repeat that once again?
Sure. So the second normalization is, okay, can you?
Yeah, this is my concern. Like you said, the customer number and the name and the shipping address. So the second normalization, the first normalization, you took the customer number and the name, and the second normalization, you took the customer type, correct?
No, I did not take the type.
Sorry, customer name and the address type. But where did the address go? Actual address. There are 3 types of addresses. So
sure.
where did you keep that address?
Let me explain it to you. So let's say I have a table. I have my customer and name and ship address. Let me call it SA for ship address, billing address, and postal address. So this is my table, right? This is my original table. I have not done any normalization on it. Okay, Sam? So
yes, correct.
Okay, so I have not done first normalization, second normalization, third normalization. This is pure data I have. Sam, could you please mute yourself? I think people will start losing my voice. So if you have any questions, let me know. Okay, I'll explain this. So you have a customer, you have a name. My shipping address is, let's say, 1, 2, and 3. This is how I have stored my information. The first normalization says that if there are any redundancy in the table, move it away. So if you look at it, I have shipping address, billing address, and postal address. For some reason, next year I come up and define something called as IRS address or something like that. I'm just making it up. I'm adding one more field called an additional address. I'm just changing the design of the table. I'm adding redundancy to the table. So the first normalization says, look at all the redundant data and try and see if you can put it in one table. So what I'm going to do is, now I separate this information into 2 different tables. I have one table which is customer and name, and I create another table. Let's call it address primary key and the address. Okay, so what I'm going to do here is I create 100 ABC, and here, before I know, what I'm going to do is I'm going to first call this customer number, address, and address type. So here the type of information I'm going to store is 100, 1, and I'm going to call the address type as shipping address. 100, sorry about that, 1 second, 100, 1, and shipping address, 100, 2, and billing address. So I have created my first normalization form, right? I have put my first normalization form into practice. I have looked at the redundant data. It's basically nothing but address, right? It's just having different names: shipping address, billing address, postal address, and IRS address. But the concept is they are all addresses. So what I'm doing is I'm segregating the data. I'm keeping the customer information separately, and I'm creating another table which contains customer with address and address type. So for a customer 100, if I want to know what my billing address is, I will look for 100 with address type equal to BA, I know what my address is. I've created my first normal form. What does the second normal form say is, now I have created this table, but I have not currently looked at another table which is called sales order. There is another table called sales order which contains sales shipment address and sales invoice address. Let's say this is the kind of information that is stored in the sales table. This is totally different table that is being created. Okay, so here I say S100 S999 sales address is ABC, not ABC. Sales address is 1000. Sales invoice address is 2000. If you look at it, this is again an address. Why do I want to store the address in sales table and also in another table here? Essentially, the data is still the same. So what does the second normalization say is, if you can identify attributes that are applicable across multiple tables. So shipping address is applicable to a sales order table. Shipping address is applicable to a customer table. Shipping address could be applicable to a salesperson also. If that is the case, it is telling me to eliminate that information. Okay, and here I make it more generalized. This table I will make it as address primary key. So if it is 100, I know that it is for a customer. Similarly, when I come here and I say S999 1000, I know now if I am looking at it, I take this information and I go and look into this table. Okay, now I know that, okay, this line is talking about my shipping address for a sales information. See, I removed the redundancy. If I had kept the sales address, shipping address and all here, if an address is changing, I have to go change it in this table. I should also go and change it in this table. So the maintenance becomes very difficult, right? So that is what second normalization is about. Look at common fields that can be applied across multiple entities. So customer can also use address, sales order can also use address. I identify the common things and I put them in a separate table, and the separate table can be accessed by both customer table and sales order. By doing this, if I were to change the address for some reason, I do it in one place, and that is reflected for my customer and for my sales order. Did I make that clear for you, Sam?
Yeah, yes, thanks.
Sure, no problem. Okay, so quickly going back here, when I do all my normalization, this is the logical model, right? At this point, as a business user, I'm perfectly alright. I look at it and say, oh, fine and dandy, I have every information. The next step in the logical model is, I say this is my high level view. Now I'm going to create the normalized entity relationship diagram. So what I'm going to do is, I create a customer, I create an material, I also create a salesperson, I create a sales entity, sales order. But now I'm not able to do the ER lines. There is one to many and all that, but you understand the concept, right? This is the relationship. But this is not the only information that's stored. Now customer has another table that is it's associated with. It could be called the customer address information that is maintained in a separate table by my normalization technology. My customer can also be related with customer bank information. I have customer information like what is my bank account, what is my bank routing number, what is. So I don't want to store that in the main table. That is all redundant information. If I can isolate it and keep it in a separate table. Now if you start looking at the table or the logical design here, it is starting to become complex. As long as it was only these four, a user could read this and understand it very well. Now I am building tables on top of it, which is getting complex. So similarly, I will go and create tables for sales order. I'll go create several tables for sales order, logically converting them into different tables. Now I'll do the same thing for material. Do the same thing for salesperson. See, what was once a very easy diagram to understand has now become a complex design. This is also still referred to as logical design. Imagine when I send this to the business user, they're going to get confused. They're going to look at all these tables and they will not understand how one is interacting to the other table. How am I going to bring the data? How am I going to save the data? It's very confusing. But this is what happens with an entity relationship model. The data is so structured that only minimum information is stored in each table, because that's how I can quickly update my customer or material or salesperson or transaction data in a database. This is how I create my logical design. Once my logical design is created and users go through a great amount of pain to understand this and approve it, we take the logical design and put it as physical design. The moment I create a physical design, talk about physical design, I am actually creating tables. All these tables that I've put in my logical display are now turning into tables. So when I talk about tables, the most important concept that I have to talk about is primary key and foreign key relationship. So now let's look at this. I'm going to keep a cleaner version. This I just wanted to explain because how entity relationship model based on normalization will exponentially become bigger. See, it started off with 4 tables. Now look at it, it is surrounded by another 10 or 15 tables. With the normalization form in the entity relationship, the tables become bigger and bigger. That is, the number of tables increases significantly. But to keep the concept clean, let's still work on customer, salesperson, material. So when I created a customer table, going back to the fundamentals of a database concept, every table should have a primary key. What is a primary key? Every record in that table should be uniquely identified by one object, one or many objects combined together. So what will be the primary value that will be stored in a customer? A customer number will be the common thing that will be referred as a primary key. Every record, so let's say customer ID, a customer ID. So let's look at some data. Customer ID, customer name. Customer ID is 100, name is ABC. Customer name is 200, BCD, 300, FDG or something like that. In this, if you look at it, for any specific reason, and one second. So let's say I'm creating 400. 400 happens to have the same name ABC. So in this case, I cannot create customer name as my unique identifier because ABC is repeating again. But if you look at my customer ID, it's always unique. One record will only have 100. Another record cannot have 100 as a customer ID. So that's the unique object that is identifying each record. So I create that as my primary key. Again, similarly, I will create another field that is primary for my sales, which is sales person ID. Similarly, I'm going to create a material ID. Okay, this is all fine. Now I created one more entity, right? Sales order. What does sales order contain? It says this customer bought this material from the salesperson, and how many quantities? I bought 10 quantities of this material for $200. So the information that is stored here is going to be like this: customer ID, salesperson ID, material ID, quantity, and amount. $100 S100 or 9999. Material ID is M100. Quantity is 10. Amount is $200. So this is the information that's stored. But if you look at it, the sales order itself does not have any primary key. What is it dependent on? It is dependent on this table, and this table. So what I'm going to do is I'm going to create 3 keys here: cust ID, material ID, salesperson ID. So what happens is these 3 IDs combinedly forms my key, primary key for this table. So the way to differentiate it is, this is called referential integrity. The customer ID from the customer table is connected to the customer ID in the sales table. A sales ID in the sales master table is connected to the sales ID in the sales transaction table. Similarly, material ID is connected to the material ID. But when I say about primary and foreign key, a key is referred to as primary key if it is the only key that is available in the table. So in the customer table, only customer ID is my primary key. When it is the only thing that is key to a table, then it is called a primary key, and the table is referred to as master table. A table with a primary key on it is referred to as master table. So this is the customer master table. Similarly, I have a salesperson master table and I have a material master table. When I say master table, what I'm referring to is it contains reference information. I have information about a customer and its attributes. It is not containing any quantity or any amount sold information. It is purely reference and informational in nature. This is the kind of data that is stored in customer, sales, and material. But what is stored in a transactional type of database or table is it not only contains association to a customer ID, sales ID, and material, but also it stores key figures. Key figures is nothing but measures. How many quantities are sold? What is the amount that is sold? A transaction contains an association to all the primary keys in the master table. So for every master table customer ID, there is a reference here in this table for material ID and sales. So these are called foreign keys to these primary keys. So this concept is referred to as referential integrity. So the moment you hear the word referential integrity, we are talking about connecting parent-child relation or parent-foreign key, primary key foreign key relationship. So this is the logical, this is the ER model. This is how an ER model is designed. I get the business requirement, identify the entities which are customer, sales and material, associate them together. When I associate them, there is a new entity that is born, which is called entity relation, which is the transaction data. How do I connect it to my master tables? So for example, what happens is I have customer ID 100, 200, 300 and 400. For some reason, my transaction, I'm trying to enter a transaction here, which is called 500 S9999 M100 30 600. When I do this and enter and save the table, do you think the table will accept this data? It will not. The reason is 500 is a value that I have entered for customer. When I do that, I am actually looking up my master table and see if the 500 actually exists in that table. If 500 does not exist in my master table, I cannot directly create an entry in my transaction table. The 500 has to be entered here. So the moment you enter 500 and say save into the database will say you are violating referential integrity. You are entering a value 500, but that 500 does not exist in my master table. I don't see a primary key with that value. So it will come and complain that you are doing a referential integrity issue. Check the table and make sure it is correct. How will you fix it? If you think 500 is a correct master but it's not here, you will add that 500 into the master table and then you will try and save this. Now it will say, okay, I identify that there is a 500 in my customer table and save it. So this is the concept of ER modeling, and this is how a transactional database is saved. But as I said in the beginning of the session, there are limitations. There is a reason why a transactional database is built, to put data into it. When it comes to reporting, there is very little reporting functionality that a transaction database can provide. So now I have created my ER model. My next logical step is my company has the same business team has come to me and said, this is great that we have a sales application sitting in our OLTP system, but we want to store historical information, take all the transactional data, everyday transactional data that is coming into the sales application. We want to move it into the OLAP application so that we start collecting historical data and then do multi-dimensional analysis on top of this report, on top of this data. So what I'm going to do is I have my 3 tables. Excuse me. And then I have my bigger table, which is my entity. So this is, let's say, this is my customer, salesperson, and material, and this is my sales order. This is all created in my ER system. Excuse me. This is my OLTP system. This is how my system is designed. Now business has come and told me that we don't just need the OLTP system. It has a specific reason it's doing that. We want to take that data and move it into an OLAP system, into a data warehousing solution, so that we just not only save the data into the system, but we use that information to provide analytical information so that the business can look at the data and make decisions on what needs to be done. So that's what needs to be done. So right here, I have to do a what is called model conversion from a ER model to an MDM model. Before I move on to MDM model, are there any questions? Is everybody clear with the concepts of what we did with the ER system, ER model? How is ER model developed for the OLTP system? Okay, so moving on to, now we have understood what this is. So I'm going to take the same scenario and see how it is converted into a MDM model. Let me actually use the same. As the name suggests, it's going to be a model that has multi-dimension. So a master table that sits in an OLTP system like SAP ERP, SAP ECC, or SAP CRM, or SAP SD, SAP FICO will get converted to a new concept called dimension. Customer, material, salesperson. There is one other additional thing that we are going to add in a multi-dimensional, which we don't really care for in an OLTP system, and that is called time dimension. Why do we need time dimension is, what is the purpose of an OLTP system? It is to store current information. It is providing information on current data. So I'm not doing any historical analysis or historical store of data. So I'm not going to be bound by time. I'm just doing a day-to-day activity. I'm only concerned about this month or today's data in an OLTP system. But what is the purpose of an OLAP system? The OLAP system, the primary reason is we want to hold historical information. So we want a dimension that is called time. A time can be a year, it can be month, it can be quarter, it can be even days. So now I have established my dimension. A customer is a dimension, a material is a dimension, time is a dimension, and salesperson is a dimension. Now I'm going to introduce a new table called sales order. If you start looking, if you look at it this way. I'm connecting my sales order to salesperson dimension. I'm connecting to my sales order to a material and time dimension. I'm connecting my sales order to customer dimension. If you look at the structure, doesn't it look like a star? There is a midpoint and it is shooting arrows in all directions. So the MDM model has another name. It's either called as MDM or it is also called as star schema. The name is because it looks like a star. Always a MDM model will have two different types of data stored. And this is one of the biggest advantage why users like MDM modeling than ER model. The reason is, I'll tell you what are the two types of data that is stored in any MDM model. One is dimension or dimensions table. The other one that sits in the middle is called fact table. No matter this example, you take any complex scenario possible for business, you will always see that there can be only one fact and it will be surrounded by dimension. It will always be a star schema. So that is the benefit of an MDM. So if you look at the ER model, the moment I started working on my normalization, look at how my table started expanding big time. But when I come to an MDM model, no matter how much complex the scenario is, I have to comprise all my information into a standard framework. So this is a standard framework. A MDM model or a star schema can only have two types of data, dimensions or fact table. How is it structured? Fact table is always in the middle and it is surrounded by dimensions. Now going back to Gurunath's question, what is multidimensional, right? So now I'm going to look at what is stored in my sales order. Sales order is nothing but it's a fact table. Fact table always keeps measure information. So I'm going to store quantity, I'm going to store amount. So these are my measures or key figures or key performance indicators. I want to know my sales by how many quantities have I sold and what amount have I sold. These are my primary measures. I want to always analyze my measures, but I want to do it from multiple perspectives. Now, like in sales order, I am storing all my data in one information. So the data is more linear, right? All my customer, my salesperson, and material information, everything is stored in one. So I can only do a linear kind of reporting on it. If look at the OLAP structure, I have created a structure where I have separated my measures from my customer, salesperson, time, and material. So I can look at quantity and amount sold from a customer perspective. I can look at it from a salesperson's perspective. I can look at it from a time perspective. How much quantity did I sell this year when compared to last year? I can do the same analysis from a material standpoint. So this is why it is called multi-dimensional. I'm looking at the same fact information from multiple views, multiple angles. So that is why it is called multi-dimensional. This is linear and this is multi-dimensional. This is the conversion from a ER model to an MDM model. So let me quickly show you. Let me go to this. Once you get access to the blogs and all that, you will be given access to all these materials. All the BW materials from SAP are available to us. It will be posted to the blog, to the corresponding places, and you will be able to access all this information. So let's quickly talk about, now you know star schema. So now when you go in outside, when people start talking about star schema, you can visualize what it is. You can say, oh, this star schema is nothing but it contains two types of tables, dimension tables and fact table. Fact table is always in the middle, surrounded by different dimensions. The reason why it is built that way is the fact can be analyzed from multiple dimensions. That is the concept. So as I said, it consists of two main tables. It consists of fact, which is nothing but quantities, amount, its key figure data, and the other one is dimensions. So any star schema will contain two types of tables, fact table and dimensions tables. So let's look at it. So again, this is the star schema, and it is commonly referred to as classic star schema. And I will explain what the classic star schema is. How is it different from a extended star schema, a snowflake star schema? There are multiple versions of star schema. This is just for the general understanding of us. We have not got into BW yet, right? So we are talking about star schema. The moment we go into modeling for BW, you have a now good base of what a star schema is. You're not starting fresh. You've understood the concept of what star schema is, and it will start building on top of that and say what are the limitations in building just a classic star schema. How will you have issues when you create a classic star schema in a BW system? How will you overcome that by creating an extended star schema? So let's wait on those for further sessions. As we move into SAP BW concepts, we will start talking about it. But for this session purpose, we are just making everybody understand what a schema is, what a multidimensional model is. So that's what we are trying to do here. So a fact table contains key information like sales, quantity, amount, and all that, and it is connected to customer ID, material ID, and time dimension. So these are three dimensions that are surrounding a fact table. Let's go further. Okay, so dimension tables, again, there are some similarities between ER model and the dimension model, right? So a customer master table in an entity relationship is now become a customer dimension in MDM model. So if I go here, again, if you look at it, customer ID becomes my primary key, customer name, city, region. But did you look at one difference in entity relationship? Just because I'm very particular about my normalization, a customer table will have the bare minimum information stored in that table. Additional information like customer address or bank information are stored across multiple tables. So I have to hop from a customer table to a customer address table to get additional information. But with OLAP systems, the OLAP systems are built to maintain larger volume of data. So the primary concern here is to read the table. So I can store the data even if there is redundancy. I want to store it in one place so that I can easily access that information. So if you look at here, I have no restriction. I created my customer ID. I have customer name, city, region, everything stored in the same dimension table. Similarly, I have material dimension table, time dimension table, everything stored. If you look at it, customer ID is the primary key in my customer dimension. Material ID is my primary key in the material dimension. And day ID is the primary key in my time dimension table. This is how I have stored my dimensions. So now let's quickly take a look at somebody's not on mute. Quickly. Okay. All right. So now we have looked at dimensions table. Now let's go into fact table. How a fact table is built. Look at the fact table. This is also very similar to the entity relationship model, whereby my fact table is maintained by the foreign key relationship with my corresponding dimension tables. So I have a day ID dimension value, customer ID, material ID. This combination makes my primary key for my fact table, and then I have my sales volume and quantity. That is how my sales fact table is built. This is how my entire star schema is built. I have the fact table in the middle. Each of my day ID is connected to my dimension table. Customer ID is maintained to my customer dimension. Material ID is maintained to my material. So this is how a classical star schema or a multi-dimensional model is created. What are the biggest advantages? Let's talk about the biggest advantages. The first and foremost is the complexity with the entire entity relationship is with normalization our tables exponentially increase, but with multi-dimensional model we always have a set framework. It has a fact table and surrounded by dimensions. Okay, now let's look at one scenario where I have built my ER system. I have created my transactional database. I have connected it with my customer, salesperson, and material in the ER OLTP system. Tomorrow there is a business requirement which says that we have identified one more information, which is, let's say, for I don't know, for example, let's say country. I want to create a new table called country and associate that also with my sales order transactional table. I have an existing design. Now I'm adding another new table to this. In an ER model, when I say that I'm going to make a change to the existing transactional design, it is a huge problem. There is a lot of issues. Again, I have to go revisit normalization, make sure everything is taken into consideration, and I come back here and make sure. But in the case of, because everything is tied together, once I want to include this country, my entire table structure changes here. I'm adding all information. But if I want to do the same thing, if I want to add a new dimension to my system, all I have to do is just create a new dimension and associate that with my fact table. Now my fact table, instead of having 4 dimension foreign key relationship, it will now have 5 relationships. But adding is that simple. It becomes very simple when compared to that of ER model. So one big advantage is the structure is a framework. There is a structured framework in MDM model. It is always a star schema model, but in the case of an OLTP system, it can expand exponentially. Second advantage is if I want to make a change to the design structure, it is very complex and very cumbersome in a ER model, but it is very fairly straightforward in the case of an MDM model. So these are the biggest advantages. At this point, I want to only let you know this information. But when we get into extended star schema, see, there is an issue. I will quickly talk about what in a schema. When we talk about schema, this is also referred to as an ER schema, enterprise relationship schema. This is called multi-dimensional schema, right? In a schema, if a customer master table is associated with a transaction table, the same customer table is not allowed to interact with another transaction table. Let's say I have another invoice transaction table that I am maintaining. I cannot use this customer to connect to this transaction. I have to create another table, and let's call it customer 1 table, and only that can be connected to a invoice. So every master is associated with its own transactional data. Look at the limitation. I cannot reuse a master data that is used in one place with the other, and that is a limitation in the classic star schema also. I cannot use this dimension if I want to create another star schema. Let's say I have another star schema I am building. My fact table is here. I cannot reuse a dimension that's pointing to another schema and use it here. This was a big limitation with a classical star schema. In order to overcome that issue, SAP BW came up with this concept of extended star schema. Extended star schema is, the problem is only when if I actually use the customer and directly connect it to my fact table, I cannot reuse it. What if I keep the customer out of my picture? I only use a pointer. I use a pointer called customer ID. Only the pointer is pointing to my fact table. The actual master table is sitting outside my schema. So it's outside here. So this schema can talk to this. At the same time, I can create another schema, and that can also talk to other customer ID and connect to this. So the master table goes out of the schema structure. Only the IDs remain as dimensions, and the dimension IDs will talk to the customer master table and get the data. So that is the whole concept of. So now you understand why it's called extended star schema. I have a star schema which has dimensions and fact. Now I'm extending the schema so that I can use the dimension across multiple schemas, and that's the concept of extended. So in this session, we have understood what OLTP system does, OLAP system, what are their limitations, how do they complement each other. We looked at that. We looked at what are the different scenarios where we would use an OLTP and OLAP system, and then after that we moved into the different modeling mechanisms used for an OLTP system and an OLAP system. An OLTP system uses ER modeling, which is entity relationship modeling. What did we do in entity relationship modeling? We get the business requirement. We first create a logical diagram. That is another significant difference or advantage of OLTP and OLAP, right? In ER model, we have to create a logical model plus a physical model. A logical model is for the business to understand, and physical model is to create the actual database table. So it's a time-consuming process for us to create a logical step and a physical step. When it comes to MDM modeling, We only have physical model. We don't have to create logical model. So that is a time saving factor. Okay, so talking about entity relationship model, we have sequence of steps. What we do is we first identify, based on the business requirement, we identify what are all the different entities that are required for the sales application. The moment we identify the entity, the second step is we identify the relationship between these tables. And then the third step is, now we have identified the entity, now we have identified the relationship between the entities. Now we identify the attributes of each entity. What makes it more meaningful? The moment we have that, once we have connected the association between the entities, a new type of entity is born, which is called the transaction entity. By interacting the salesperson with the customer through the material, we have created a sales order transaction. But when we do the ER model, what we are doing is, the main benefit of an OLTP system is to insert, update, and add data. So in order to make that very efficient, we go into something called as normalization of tables using ER mechanism. When we do normalization, we try to eliminate all the redundancy possible, so that the data is stored in each table is very minimum and it is very quick to perform add, delete. But the disadvantage with this, the advantage at the physical level is that the data is stored very quickly and efficiently. But the disadvantage is, as the tables grow larger and larger, that is, as it expands exponentially, it becomes very difficult for the business users to understand, to keep track of what information is stored in what table. Those are all the limitations of OLTP systems. So we take that information and we know that the transactional data that is stored in the OLTP system is very linear in nature. It does not give us many dimensional data. So in order to overcome that issue, we moved into another concept called OLAP system, which is for primarily analytical reporting. For analytical reporting, what are the primary factors is, we need larger volume of data, historical data, to be stored in the system. But just holding historical data is not sufficient. We want to look at that data from multiple perspectives. We want to look at it from customer perspective, we want to look at it from sales perspective, material, time, all this information. So for that, we cannot use a ER model. The ER model is designed to be highly normalized, and it is specifically maintained for a specific business functionality. So in order to do the analytical side of it, we went ahead and created something called as a multidimensional analysis or multidimensional modeling mechanism. What is a multidimensional modeling? It primarily contains of two tables, dimensions and fact table. What is dimension? Dimension is nothing but a representation of the master data, but it is also a point of view, a customer point of view, a salesperson's point of view, a material point of view, or a time point of view. What is fact table? Fact table contains the actual key measures like quantity and amount. And if you look at the structure of it, it is always a standard structure. It always contains a fact table in the middle, and it is surrounded by dimensions. The advantages of an OLAP MDM model is, it is a structured framework. No matter how many dimensions there are limitations on how many dimensions you can add, but we will get to that when we go into SAP BW. For the time being, to understand the high level concept, a dimension can be added at any point of time. It is less complex when compared to adding a dimension in the adding a table in the ER mechanism. That is the structured framework. It is always having multiple dimensions with the center fact table. These are all the, and then comes the concept of extended star schema, where if you want to share a master table or a dimension with another schema, there are limitations with the classical star schema. So we will explain when we go into SAP BW sessions. We will talk about what the limitations are and how we will overcome it using a extended star schema. So these are the main things I wanted to cover for today's session. Any questions? Okay, if there are no more questions, I think we can wrap it up for tonight. So for the next session, yes, David, do you have a question? Or do you want to wrap it up for today? I'm not sure if your S is for wrapping up or for asking a question. All right. Okay. So let me quickly take 2 more minutes and explain. No problem, David. All right. So now we have set the base for our BW training. Everybody is, I think, now the concept of what a data warehouse is. I'm hoping that that is completely drilled in all of your systems. What is a data warehousing system and what is a traditional OLTP? I think I have discussed it enough so that everybody will even have dreams of OLTP and data warehousing system. We have looked at it several times. We have understood what these two systems do. Yes, David, what is your question?
Can you hear me?
Yeah, I can.
Oh, thank you. Could you please explain the extended star schema again and the difference between the star schema? I mean the concept of the pointers.
Correct.
And
I can definitely talk about it, but the reason why I didn't go much into extended star schema is, David, at this point I wanted to only show the difference between an OLTP system and OLAP. If I talk about extended star schema now, you should understand what an info object is in a BW system. What is an info object made of, and how is it designed, so that I can explain on top of it what an extended star schema is. Then you can actually visualize what I am talking about. If I give you an explanation now, it will be a little vague for you, because when I talk about pointers and all that, you're not visualizing what I'm talking about, right? But I can quickly give you a recap of what extended star schema is. Let me go to a new slide. So now you understand the concept of, I have a fact table. Let me put it as a cube. I have a fact table surrounded by dimensions. And each of them are connected to my fact table. Right? So let's say this is my customer, this is time, salesperson, and this is material. Okay, so this is my original star schema. I have the customer ID. I have the primary key here, which is customer ID. I have a primary key here, which is, I have a primary key here, which is called day ID. I have a material ID, and I have a sales ID. So when the star schema, classical star schema is created, I take the customer ID value itself. Let's say if it is 100 here, I take the value 100 and store it here. Similarly, if my material is M100, I store that value here. If my salesperson is S999, I store that here, and my day is 2012, I store that information. So now if you look at it, I have a physical connection established to my customer table, right? Because I'm pointing, there is a primary key foreign key relationship that has been established. For a customer ID that is sitting in my customer table dimension, I have an associated foreign key sitting in my table. So this table is being locked by this data. I have 100 accessing this table. So at the same time, if I decide to create one more star schema, and I'm saying, okay, now I want, this is an invoice fact table, and I want to look at the same customer ID, and I bring the information. Here, this information is already within a schema. They are already physically connected to each other. From an outside schema, I'm trying to get into another schema and pull this customer data. So in a star schema, that is not possible. Only a physical connection can be made within one schema. If I'm outside the schema, I cannot physically connect to this table. To overcome this, what I'm doing is, I'm creating something called as extended star schema, and I'll show you what it is. I create something called as customer. The customer has a customer ID, right? This is my primary key. In addition, I create something called as a surrogate ID. I create a surrogate ID which is in addition to my customer ID. If my customer ID is 100, so this is how my data is. I have customer ID and my surrogate ID. Customer ID is 100. My SID could be A1. Okay. What happens is when I'm creating a schema, this customer along with this customer ID is outside my star schema. The only thing that is pointing is my pointer, which is my surrogate ID. My surrogate ID is connected this way, and my surrogate ID is also connected this way. So here, instead of storing the value 100, I will store A1. Now A1 I know is pointing to the SID table, which contains the value A1. But A1 does not make any sense. A1, now if I connect it to 100 to this table, I know A1 is equal to 100 in my customer. But I'm not directly looking up the physical table customer. I'm only using a pointer that will look up this 100 value. So since I'm not directly looking up, this table is always free. It is not specific to one schema. Now I can go ahead and create another schema, and I can still use the same concept. I can use a SID table. The SID table will point to the customer. So that way I am removing my dimensions out of the schema. I'm making it schema independent, and any schema can touch on it. So that's why it's called, using the schema, I'm extending my information outside the schema. That's why it's called extended star schema. Did I answer your question, David?
Yes, thank you.
Sure, no problem. All right, so let me quickly go into this. So we have created our baseline. We have talked about all the information that are required to go into the SAP BW. So starting next session, we are going to go into the BW system. First, quickly, maybe I'll spend maybe 20-30 minutes talking about the screens. Most of the candidates in the class would be new to the SAP tool itself. So I'll spend maybe 15 minutes going into the system, showing what the different screens are, what are the common screens that we would go into. I'll talk about all that information so that you get comfortable with the screens. If I directly say I'm going into RSA1 screen or something like that, it might sound a little new and confusing. So I'll just slowly lead you into the screens. I'll show you quickly what are all the different commonly used screens in BW. Then we will go into modeling. Now that we have understood the basics of ER model, we have understood the basics of MDM model. Now if I go into BW system and start talking about modeling for SAP BW. When I say modeling, we cannot directly, tomorrow we cannot jump into SAP BW system and say, okay, I'm going to create 10 tables that is going to bring data from a transaction system into it. There are going to be logical steps, right? When we talk about modeling, so what we are going to talk about, what are all the building blocks that are, so in a transactional database, normally a table is a transparent table. A table will contain several fields. Each field is referred to as a column or a field. But in BW terminology, they are referred to as info objects. So we'll talk about what info objects are. How are they defined? How is it designed? What comprises of an info object? There are characteristics info objects. that hold character information. There are key figure info objects that hold key figure information like sales, quantity, and all that. So we will slowly start building on this information. We'll talk about info object. When a brick is built for the house, what is the next level? We build several info objects. So several bricks are put on top of the house on the foundation. Once that is done, then we start building the next level of the house, which is too many building blocks collected together will now raise a house. What is a house? It is nothing but a cube, an info cube. So now we have small pieces that are required. So we created all the small pieces. All the small pieces combined together will become the data warehousing. So it will create cubes, data store objects, different objects will be created on top of info objects. So we will slowly look at that. In the coming sessions, we will be looking at the building blocks modeling piece of it. Once we cover that piece, we will start with a simple example of an extraction process, ETL. So no matter what session we are in, we will be focusing on three primary functions of a data warehousing: modeling, ETL, and reporting. The first or I would say first half of the sessions, I would say for the next 10 sessions or so, we will be primarily focusing on modeling and ETL, because it doesn't really make sense for us to talk about reporting at this point, because reporting comes at the end. If we don't do the modeling properly, if we don't do the ETL processing properly, we're not going to get the data for reporting. So reporting comes at the later part of the sessions. Now our focus will be modeling, how to create different objects differently according to business requirements. And then once the objects are built, how are we going to connect it to the OLTP systems and bring in data? It could be an OLTP system, it could be a flat file, it could be another BW system from where we are bringing data into this BW system. So there are several ways to extract data. We'll be looking at those information. So that concludes our session for tonight. This Friday, I will not be able to take a session because I'm out in Newport, New Jersey. I've been doing an implementation for the past 2 weeks, so I've not been close to my family. I'm actually traveling this Friday. I'll be reaching home close to midnight, so I will not be able to take a session. So the next session would be on Monday. So from Monday onwards, I'll be local again. So from Monday, we will have the regular session, and I'll see if I can add few, maybe 20 minutes or 30 minutes here and there during Monday, Wednesday, Friday session to see if we can compensate for the Friday class that we are missing. Okay, so just wanted to give you all a heads up so that you can plan your Friday evening. You don't have to be sitting and waiting for this. You can plan your evening for Friday. All right. Are there any questions? Are there any questions?
No, thank you.
Man. It's a great lesson, and see you on Monday.
All right. Thank you so much, Rafiq. So I'm going to be talking to you guys on Monday. So have a great weekend. I will talk to you guys on Monday. Thank you.
Thanks, Aman.
Thank you.
Thank you, Sunil.
Thank you.